So de novo drug designing is designing a novel lead molecule based on structure of the binding site. Okay, so it is a kind of amalgam of structure based and ligand based drug design. So we should know the 3D structure of the drug target. It's a very base for proceeding with the de novo ligand design. Okay, so here let me slightly zoom this. So this is what I defined. A design of novel lead compound based on structure of the binding site. So if you want to know the structure of the binding site, then we have to solve the 3D structure of the drug target. Okay. So already I explained you what are the different ways by which we can solve the 3D structure of the drug target. So we have so many experimental methods, like we have X-ray crystallography, we have nuclear magnetic resonance spectroscopy, we have electron microscopy, right? So these are the various commonly used technique for solving the 3D structure of the drug target. So that's the starting point of this de novo ligand design or fragment based drug design. Both are slightly different, but conceptually they are same. Hope my voice is clearly audible, right?
Yes, sir.
Okay. So the very first step is we have to crystallize the protein molecule along with ligand. Very important. So if you want to go for molecular docking, even if you have the protein molecule alone, that is well and good. But if you go with uh, de novo ligand design, definitely you have to solve the protein molecule along with some known inhibitor. Okay, so that is very important. So that is the crystallization of protein along with the ligand molecule, right? So once if we know the 3D structure of the drug target along with known inhibitor, the next step is determining the crystal structure. We have to solve the protein along with the ligand molecule. So this we already discussed, right? So the basics of X-ray crystallography. First we have to form the crystal, then we have to pass the X-ray. So diffraction will takes place, and we capture the diffraction, right? So once if you solve the structure, then we can easily identify where the binding site is present. That is the third step. Where the binding site is present, we can easily find if you crystallize the protein along with the ligand molecule. So for example, this is the protein molecule that is crystallized along with the ligand molecule. So we can say this is the binding site of this protein molecule, right? That is the intention, that always the drug designers will be interested on solving the protein structure along with known inhibitor or the drug molecule. So identification of binding site is the third step. And fourth step is, so once if we identified the binding site, then we can easily get to know that what are the type of interactions taking place between the drug molecule and the protein molecule. So identification of the binding interaction, that is the fourth step. So once if you did up to fourth step, so then we have to separate the protein molecule and the ligand molecule. This is what actually I did and gave it for you for your second exercise and third exercise, flexible docking and rigid docking. So I took the complex HSG1, so which is a complex of HIV protease along with some inhibitor called as indinavir, IND. So what I did was, like, I separate the protein molecule and ligand molecule. Same thing we have to do for the de novo ligand design, drug design. So fourth step we have to we sorry fifth step we have to remove the ligand molecule from the binding site. So we'll be having two files now. One is the protein file, another one is the ligand file as a separate file, but that is actually a complex. Okay, the atomic coordinate is complex, but no, manually we have separated the protein molecule and the ligand molecule. So next step is that, based on the known information what we have so far, we have to design the ligand molecule to fit inside the binding site. So then we had to calculate what is the binding strength of the newly designed ligand molecule. Then we have to check the synthetic feasibility of the design molecule. Since that molecule is not exist, it's going to be very novel molecule, right? So we have to check whether the molecule can be synthesized or not. So once if it can synthesize, and then we had to evaluate the molecule using in vitro and in vivo studies. Then we have to optimize the structure. if there is a lack of absorption, distribution, metabolism, excretion, or lack of efficacy, then what we have to do is that we have to optimize the structure, right? So this is the pipeline that is followed for de novo drug design. Is that understandable?
Yes, sir.
Okay, so yeah, let me explain each step in detail, right? So just like docking, right? So while discussing the docking, we said that there are two types of docking algorithm. One is called as manual, another one is the automated. Very similar to that, we have two type of de novo ligand design algorithms. A few algorithms which are manual and few are automated. So let's see what are the major differences between the automated and the manual one. So manual is preferred by the expert, right? So if you are a very experienced person, then you can go for the software that deals with manual de novo ligand design. If you're a very beginner, if you don't have very good knowledge in chemistry or synthetic chemistry, medicinal chemistry, then it is better to go with the automated. The main difference is in case of automated, the program is completely automated, so there is not going to be any bias by the operator, right? So which means that if you are a medicinal chemist or if you are a synthetic chemist, right, or if you are a pharmacologist, you may already have some idea on your mind, and you may try to impose that idea to your ligand molecule. But in case of automated, it is taken care by the algorithm itself, so there is no possibility for any bias. That's why it's called as there is no bias in case of the automated procedure. And this automated procedure is very much useful if you want to generate large number of lead molecule. Say you want to design some thousands of lead molecule, 1000 or 2000 lead molecule, right? Then that's a large number, right? So we can go for the automated method. In manual method, we cannot design many number of molecules. Very few molecules we can design using the manual option. As I said, that it is going to produce very novel structure. Sometimes those structures may not be synthesizable. Okay, so we have to look into the structure, and we have to discuss with the synthetic chemist, organic synthetic chemist, to check the feasibility of synthesizing those molecule. uh, uh, Also in case of automated, right, so they do not use very stringent scoring function for calculating the binding energy, right? So the scoring function, scoring structure for binding strength calculation is mostly unreliable in terms of the automated de novo ligand design algorithms, right? So coming to the manual one, so operator directed study, and it allows the input for a designer idea. This is a key point, right? So it has no advantage as well as a disadvantage. This is considered as the major advantage of manual method, in which the user, okay, so what they can do is that they can implement whatever idea they have. So if you have some idea on your mind that your lead molecule should look like this, or it should contain this chemical moiety, or the scaffold, that can be enforced, implemented in the manual, cannot be done in the automated. So this is useful only if you want to design very few number of molecules, one molecule or two molecules, then we can go for the manual method. And the manual procedure is very slow, and it is very limited to the designer's originality. There is no big contribution by the mathematical algorithm behind that. So everything will be implemented only by the human ideas, right? So that is the difference between manual and automated, right? So there are certain points that we have to consider while working with the de novo ligand design. Again, I repeat, I said in the previous class also that we have a lab session for de novo ligand design. Okay, so you'll be doing practically some ligand design using the de novo ligand design algorithm called as lig builder algorithm, right? So what are the points that has to be considered? So these are the points you have to consider while doing the practical session also, right? uh, so we have to avoid designing structure that completely fill the binding site. Again, I repeat, so we have to avoid designing structure that completely fill the binding site. Okay, the reason for this is that later you may want to optimize the structure. Okay, so if you want to optimize the structure, then there should be some space for including some functional group or deleting some functional group, whatever it is, right? So you studied various strategies of lead optimization, right? So starting from varying alkyl substitution, varying aryl substitution, then ring expansion, ring contraction, chain expansion, chain contraction. There are so many things, right? So bioisoster, isoster, rigidification, simplification, right? So whatever you wanted to do, right? So we should not fill the complete protein binding site. That is not advisable. Very important point you have to consider, right? So there may be some experimental error in the crystal structure. Already I told that we cannot completely rely on the crystal structure. The quality of the crystal structure, that depends on at what resolution they have solved the structure, what's the R factors, so many factors, they're going to decide the quality, right? So we have to ensure that the input structure, protein structure that we are using is of very high quality. Otherwise, uh, the error that is present in the structure, protein structure, will be transferred to the output of the de novo ligand design. Um, there may be different conformations that can be fitted inside the binding site. That is another reason why that we should not fill the entire binding site. Okay, so this kind of algorithms are kind of it uses the same principle what I discussed for molecular docking using UCSF dock. So kind of rigid body docking, right? Same kind of principle is used here. But naturally the protein molecule and the ligand molecules, they are highly flexible in nature. So there should be some extra space we have to give for the conformational change that can take place within the binding site for the ligand molecule. So as I said, that space needed for the drug optimization, right? So these are the thing. uh, Flexible molecules are better than the rigid molecule, right? So which means that while designing we have to think of uh, uh, you know having more carbon carbon single bond rather going for ring system or double bond or triple bond. Okay, so if the molecule is flexible, so that will allow alternate the binding modes. So some conformations may have higher binding energy, right? So that's why we have to think of flexible molecule rather going for the rigid. So this again and again I am repeating that the main disadvantage of going for de novo ligand design is that the molecules which are designed using de novo ligand design may be completely novel, may not exist already, right? So if it is completely novel molecule, then we have to think of how easily the molecule can be synthesized or how much feasible synthesizing the molecule. So these are the points we have to consider. So there are different methods by which we can evaluate the synthetic feasibility of the newly designed molecule using de novo ligand design. So another point is no one much care about this, but this is very important for advanced researcher in drug design, right? So whenever we say that the molecule binded to the protein inside the binding site, so what is the stability of that conformation? Okay, how much stable is that conformation, right? So that we have to check, because the molecule may not be preferred if it is not a stable conformation, right? So it should be either global energy minimum conformation or at least some local minima. So those conformations are considered as a stable conformation. So we have to think of whether you know the ligand that is generated within the binding site is having stable conformation. So these points are important only because we are designing the drug molecule based on the binding site. There won't be any issues, conformational issues, if you go for molecular docking and all. Because the molecular dockings and all, you may remember we gave 10 or 20 runs genetic algorithm, right? So it is going to output only the 10 or 20 best possible conformation, not all the conformation, right? But in case of de novo ligand design, it won't think of whether the conformation is stable or not. The intention of the algorithm is bringing some new molecule that can be fitted inside the binding site. So manually we have to check whether the conformation is stable or not. So energy of desolvation again, it won't deal with any desolvation energy. So we have to think of the desolvation energy. I'll be discussing that later, not in the session, some other session, right? um, so structural differences in target from different species, no need to much bother about that, right? So these are the points that we have to consider while going for de novo ligand design. Is that understandable?
Yes, sir.
Yes, right? Okay, so far I think it's easy, right? So we have many number of de novo ligand design algorithm. So as I said that we'll be using link builder for the practical session. Since link builder is free open source, right? So we can use it. There are some commercial softwares which are also available. Something like, for molecular docking we have Autodock, which is free. We also have Glide FlexX. Glide is the product of Schrodinger. We have FlexX, right? So these are commercial software, right? So obviously there will be slight difference in the algorithm. Commercial softwares will perform better than the free, right? Not always, right? So uh, one such commercial software is LUDI. So LUDI is very famous de novo ligand design algorithm program developed by Discovery Studio. I think you already installed Discovery Studio Visualizer, right? So the same company, Discovery Studio, they came up with this algorithm called as LUDI algorithm for de novo ligand design. LUDI algorithm for de novo ligand design. So this LUDI algorithm is a kind of automated program. So we can easily automate the procedure, right? There is no much manual intervention in case of LUDI algorithm. Just one or two steps. We have to input the protein ligand complex as a separate file. Protein as a separate file and ligand as a separate file. That is the input for this LUDI algorithm. So what this algorithm does, it identifies the possible interaction site first. Since we are giving the protein molecule complexed with the ligand molecule as a separate file, so first it will identify what are the interactions made between the protein molecule and the ligand molecule. So wherever the amino acids which are participating in the bonding, and wherever the atoms in the ligand molecule which are participating in the interaction, so those points will be captured as pharmacophore element or pharmacophore feature. Again I repeat, very basic. We had to input the protein molecule and the ligand molecule as complex. Most probably it should be experimentally determined structure using X-ray crystallography or NMR, any method. So once, if you input it, since it is automated, so it takes the protein ligand complex structure. First thing what it does is it identify the possible interaction between the protein molecule and the ligand molecule. So which amino acids are interacting with which atom in the ligand molecule, those informations will be captured, and that will be labeled as the pharmacophore element or the pharmacophore feature. So which means that that interaction is important. That is what is assumed by the algorithm. So what next it does, so it know that uh, what the known inhibitor is, how the known inhibitor is fitted inside the binding site, what kind of interaction it makes. So based on that knowledge, it will try to change. It takes some different small fragments and fit it inside the binding site in the very same way, like how the existing inhibitor or the drug molecule is co-crystallized in the complex structure. So it takes molecular fragments and fit in different region within the binding site. So as I said in the previous lecture, that molecular fragments, right? So the molecular weight of this molecular fragments will be very less comparing to the drug-like molecules. So if you take drug-like molecules, they'll be having the molecular weight in the range of 500, 600 Dalton. But this fragments will be having much lower molecular weight, maybe in the range of 100, 150, 200 Dalton. So different fragments will be fitted inside the binding site, and then later each fragment will be linked. Okay, so some functional groups will be used for linking each fragment. So these are the basic major steps of LUDI algorithm. So we'll see more detail. This is a pictorial representation of what I discussed so far, right? So we have three major steps in LUDI algorithm. So this is the first step. Third step, same thing what I explained, right? So very first step is that it has to capture the interaction site. So we input the protein molecule, ligand molecule, complex structure. Okay. So once if we input this, so it identify the interaction site. So identification of the interaction site is the first step. So this is what I said as pharmacophore element identification or pharmacophore feature identification. Both terms are same. So here different types of representation you can see in this image one, left hand side top, right? So you can see some regions which are having dotted dots, right? That is one way of representation. So the another representation is like this: XY, XH. This is another representation, right? So another representation is something like this. Some amino acid functional groups are labeled here. So this is the way how the interaction sites are actually mapped. So what is this dotted point? So this dotted points are some hydrophobic feature is there. Some aromatic or hydrophobic feature is there. Again, I repeat, the dotted points which represents that pharmacophore site is aromatic or hydrophobic in nature. So coming to this XY, this XH, so this corresponding for hydrogen bonding interaction site. This corresponding for hydrogen bonding interaction site. So this NH, this O. Okay, so these are functional group indirectly that dictate that some hydrogen bond donor is present here, some hydrogen bond acceptor is present here. And this is the way how very first step, this is a way how the interaction sites are mapped by the LUDI algorithm, right? So let me add few more points related to that. So once if you fit this is the binding site. Okay, this is the architecture of the binding site of the protein molecule of the receptor. So once if you design a drug molecule, the drug molecule should have some hydrophobic group here. First understanding. So again, it should have some hydrophobic group here. It should have a hydrogen bond acceptor here. It should have hydrogen bond donor here. That's all. Okay, so based on the key feature which is mapped, we can say that there are four important regions for the ligand molecule. First region, we need some hydrophobic or aromatic group. So here also, second region, we need some hydrophobic or aromatic. Third region, we need hydrogen bond donor. So here we need hydrogen bond acceptor, right? So hydrophobic, no issues, right? So how the algorithm know that there should be a hydrogen bond donor here? Because it mapped this oxygen on the binding site. So if there is a hydrogen bond donor, then that can make participate in hydrogen bonding. So similarly, how it knows that there should be a hydrogen bond acceptor here? That is because there is a hydrogen bond donor very close to that. So the drug molecule should contain a hydrogen bond acceptor at this position. Is that understandable? So this is what is called as mapping the interaction site, the first step of LUDI algorithm. Is that understandable?
Yes, sir.
Okay, so moving on to the second step. So there are any de novo ligand design algorithm will be having two databases. Okay, they will have two databases. One is called as fragment database, and the another one is called as link database. Again, I repeat, any de novo ligand design algorithm will have at least two database. One is called as fragment database, another one is called as link database. So what's the difference between this fragment database and link database? This fragment database will have the structures of small fragments whose molecular weight may be ranging from 50, 100, 150. Okay, in that range it may have, right? Very small fragments. So this, okay, so here if you look at this structure, right? So 5-membered ring with NH, that is a small fragment. So here if you look at this, a phenyl ring or benzene ring, that is a fragment. So here if you look at this cyclic structure, 6-membered ring with carbonyl group, C double bond O, fragment. So three fragments which are fitted inside the binding site. This is not random, right? So if you carefully look at why this three fitted inside. So if you look at fragment, this fragment is complementing with the hydrophobic region of the binding site. The benzene ring, it can participate in aromatic or hydrophobic interaction. So there is a kind of complement there. So if you take this one, so this 5-membered ring, it can participate in. Is my cursor visible for you?
Yes, sir.
Okay, actually, I think I am not moving. Is my cursor now visible?
Yes, sir.
Okay, so this 5-membered ring is aromatic in nature, so it can participate in the hydrophobic interaction. So why it specifically taken this 5-membered ring with NH group? Because if we fix this, it complement two region. One is this hydrophobic region, another one is it can also participate in hydrogen bond. So the ligand here, the fragment which is fitted here, it can complement with this hydrophobic region, as well as it can act as hydrogen bond donor. So there is possibility for hydrogen bonding between this group. Similarly, if you take here this 6-membered ring, it can act as, it is having a carbonyl group, it can act as hydrogen bond acceptor. Not necessarily here we have to fix this uh, uh, 6-membered ring, it can be anything. Just we have to complement uh, whatever we have captured in the first step. Interaction site should be complemented. That is a second step. So once if you fit this type of fragment, we cannot say that we got the complete structure, right? So still it's a very small fragments which are sitting inside the binding site here and there. So we have to join those. So for joining those fragments which are fitted, so they have another type of database that is called as a linked database. So the main difference between fragment database and linked database is the molecular weight again. So linked database will be having even smaller molecular weight functional groups, which can be used for connecting any two fragments which are kept inside the binding site. So here we can say that this group is a link group, this is a link group. The other three components are the fragments. So three fragments which are fitted, which complement with the binding regions of the binding site, and those three fragments are now joined together through some small functional groups like alkane, alkene, alkyne, many groups, right, which can be used for linking. So those are called as the linker, which are present in the linked database. Is that understandable?
Yes, sir.
Okay, moving further, right? So I think no need to explain. I explained this detail, right? So we can skip. Okay, the point is that how actually it map this region. Okay, as a bioinformatician, right? So you can also write some program. It's not so complicated. It's very simple, right? So you can also write some program. So the question of interest is that how the LUDI algorithm, which map the interaction site. Okay, so that is what we have to see. So very basic idea of how it map the interaction site. So there are two types of interaction it is mapping. One is the van der Waals interaction here. Another one is the hydrogen bonding interaction here. So LUDI algorithm, which mainly focuses two types of interaction. One is the van der Waals interaction. Another one is the hydrogen bonding interaction. So let me tell that how it map the van der Waals interaction, right? So this is the binding site, and say the binding site is having some methyl group. So what is the nature of methyl group? Is it hydrophobic or hydrophilic in nature? Methyl group.
Hydrophobic.
So it is hydrophobic in nature. So this hydrophobic group, it can participate in the van der Waals interaction, right? Or hydrophobic interaction. So how that is mapped by the LUDI algorithm. So first it actually constructs some sphere, surrounding sphere. Okay, so this sphere is made for all the hydrophobic groups, right? So it makes the sphere. If the side chain of this is actually the binding site, within the binding site, there is a side chain of amino acid CH3. So can you tell that which amino acid will be having CH3 as the side chain? Which amino acid will have CH3 as the R group side chain? Okay, this is alanine, right? So probably this region, what they have highlighting here is the alanine, side chain of alanine, right? So methyl group. So they draw a spear around the side chain of the alanine methyl group. So for 4 angstrom distance, right? So for defining the interaction site, so they make some dot like this. Here you can see. I hope that is visible for you, right? So they make some dot, right? But you know this van der Waals interaction can takes place only to certain limit. So we have to trim the spear. So after making the spear, after making the dot, no, they trim this region, because if it is very closer, it cannot participate in the van der Waals interaction. So they cut this, they trim this region. So the interacting group should not be present here, anywhere here. Now the understanding is that there is a methyl group in the binding site. Okay, so if your ligand is present anywhere here in this range with a hydrophobic characteristic, then it can participate in hydrophobic interaction with the methyl group, right? So that is how they actually map this interaction site for the hydrophobic region or the van der Waals region, right? So coming to how they map for hydrogen bonding interaction, we cannot use the same concept because the formation of van der Waals interaction, that depends only on the distance. It's not directional. It can take place in any direction. But if we take the hydrogen bonding interaction, so while discussing about the Lipinski rule, I think I already discussed this. It is both directional as well as distance dependent, right? So for the formation of hydrogen bond, direction, both direction as well as the distance, they are very important, right? So how it map? Say the binding site is having C double bond O, C double bond O. So can you tell that which amino acid will be having this C double bond O? Which amino acid will have this C double bond O? Yeah, somebody can respond. Which amino acid will have this C double bond O? Prakitesh.
Yes, sir.
The question is for you.
Sir.
Hmm?
Sir, aspergine.
Aspergine. Aspergine is a basic amino acid, right? Aspergine.
Yes, sir. Then glutamic acid may have CW1.
Glutamic acid. Okay, so can I say that all the 20 amino acids will be having this carbonyl group? Yes or no?
Carbonyl.
The question is for everyone, not only for Prakash. Can I say that all the 20 amino acids will be having this carbonyl group or not? CW1O. Shashank.
Yes, sir.
Yes, all the 20 amino acids will be having this C double bond O in its backbone. Okay, so very few amino acids will be having the C double bond O in its side chain. Okay, that is what Prakatish said. That is the some acidic functional groups like aspartic acid, glutamic acid. Even what he said is right, asparagine, glutamine. Okay, so they are the functional groups that will be having the C double bond O in its side chain, right? Okay, so any of the amino acid, right? So it can be either backbone or side chain, doesn't matter. Don't think that the side chain alone can participate in the interaction. There are many cases in which the backbone of the amino acid it can participate. So any amino acid that has that C double bond O. So here the lone pair of the oxygen is given, right? So we have two lone pair of electrons, right? So now, so probably this group will be having slight negative charge, right? So if you have XH, some hydrogen bond donor, so this group is acting as hydrogen bond donor. This is also acting as hydrogen bond donor. So since we have two lone pair of electrons, so this negative charge can interact with the slight positive charge on this hydrogen and slight positive charge on this hydrogen, right? So this is what is called as the distance. The distance between this hydrogen to this lone pair of electron or the oxygen is 1.9 angstrom, and the distance between this hydrogen to this oxygen is also 1.9 angstrom. Okay, so distance is important. If the distance is larger, then they may not be participated in the hydrogen bonding interaction. The distance between this X to H is 1.1 angstrom, and this X to H is again 1 angstrom. So here it indicates it is distance based. So coming to direction, if you look at the direction angle made between this oxygen, this bond O to this hydrogen. Okay, so this angle is 120 degree. Again, this angle is also 120 degree, right? So if it is 150 degree, can it form hydrogen bonding? No. If it is 180 degree, can it form? No. Okay, so it should be in the range, right? So there is a range for that, right? So it should be in the range. So required bond angle is there, required bond distance is there, right? So if that is captured here in the first step, all right? So if the angle and if the distance is there, then those regions will be captured as hydrogen bonding acceptor or hydrogen bond donor region. And this is how actually the LUDI algorithm which capture the hydrogen bonding site. So once if it captures the van der Waals interaction site and hydrogen bonding interaction site, so as I shown in the image in the first step itself, the next step is fitting the molecular fragment, right? So there will be, I'm talking about this step, second step, fitting the molecular fragment. So it has a fragment database, a huge database. So whatever structure you are seeing here, right? So all these are some fragments. We cannot call it as drug-like molecule because we know that these are very small comparing to the drug-like molecule. If you calculate the molecular weight, this all the fragments in the fragment database will be having very small, less uh, molecular weight comparing to the drug-like what we screen in high throughput screening, virtual screening, right? So this is what is called as fragment library. Each algorithm, commercial, free, those molecular fragment library will differ. Okay, so depending upon the synthetic feasibility, depending upon the experience, they may put which fragments are suitable, right? So anyway, this fragment will be having many number of fragments. That's the point, right? So each fragment will be taken and fitted inside the binding region, which is identified in the first step. That is how they get this type of thing. Don't think that we can put only this group. This group can be replaced by any other group. Okay, the algorithm, the idea of the algorithm is that it has to pick what are the possible groups that can be fitted here. Okay, so this is one molecule. Like that, we can fit in different combinations in different location using different fragments which are available to come up with very novel many number of molecules. Okay, that is the fitting molecular fragment. So okay, so here you can see how the molecular fragment is fitted. So this region, hope you can understand that this is hydrogen bond acceptor. Uh, this is also hydrogen bond acceptor, right? So the binding site is having a hydrogen bond donor. OH group is there. probably some hydroxyl containing amino acid side chain. And here we have again hydrogen bond donor. So here we have some van der Waals region or hydrophobic region. So there are two patches of van der Waals region or hydrophobic regions here. So we have to go to this fragment library and we have to search for which fragments can be fitted in each position, right? So that's a fitting process. So if you take this, one of the fragment that is fitted in the fragment library, exactly you can see how well it is fitted, right? So CH3 group is kept here. The dotted points represents the hydrophobic region, right? CH3 can participate in hydrophobic region. So another CH3 group of the same fragment is complementing with this dot, again a hydrophobic region, and it has a carbonyl group C11O which is complementing with this OH. OH is acting as hydrogen bond donor, and this carbonyl group it can act as hydrogen bond acceptor. Similarly, the same group is kept here, right? So the oxygen it can act as hydrogen bond acceptor here, right? So this is what is called as the fragment fitting. So once if you fit the fragment, right? So once if you complement all the binding regions which are identified, once if you complemented those regions with different types of molecular fragments in the fragment library, the next step is that we have to make the connection between the fragment. So how to make the connection, right? So the LUDI algorithm it follows identifying the closest fragment. So since you'll be having many number of fragments, small fragments, so which two should be connected? The basic logic that is used by LUDI algorithm is that identification of the closest fragment. So within the binding site, you have to look for which two fragments are having which two fragments are present close. The distance is very small, so that is called as the closest fragment. And once if you identified the closest fragment, and you had to identify the closest hydrogen, very important. So while doing the practical, all this you have to consider, right? So which two fragment has to be connected? The two fragments which are very close to each other. So how to make connection between them? You have to find out that which two hydrogen in the closest fragment or closer, right? So that we had identified. Then those hydrogens are labeled as the connection point. Okay, these are called as the link point, which means that these are the places where we have the hydrogen that are closest to each other, right? So two fragments. So that those red color points are called as the link point. Now the database search. Now the algorithm search for another database called as bridge link database. So link database will be having some small fragments or some small functional group like this: alkane, alkene, alkyne. So I try to find out what is the distance between the two link point, and which of the linker which are present in the link database is suitable for making connection between those link point. So that will be chosen as the linker, and that will be used for connecting the two link points. That process is what is called as the bridging or fit bridge. Is that understandable?
Yes, sir.
Okay, so that is the third step, right? So this is an example for fragment library. So if you compare this with the previously shown, sorry, this is a fragment library, and if you compare this fragment library with this uh, 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 fragments in the bridge library, right? So these are very small, some alkane, varying chain length, right? So nothing else, right? They have only very few number of atoms, so very much the molecular weight will be very smaller comparing to the uh, fragment library, right? So any of this component can be used for bridging the 2 points, link points, right? So one case study is that time delayed synthase inhibitor is a real time example that. So for designing the inhibitor for this thymidate synthase kinase, they exactly used this de novo ligand design approach, right?